Hi guys, welcome to another lecture in the series Medicinal Chemistry 1, and today we're going to be talking about general and local anesthetics. So you may have seen, and you will definitely see throughout this lecture, both the spelling as anesthetics with a A or without the A. Well, the A is the British spelling and the absence of the A is the American spelling. So general and local anesthetic drugs, they're used to block the transmission of pain. So if you're doing a surgery, you definitely need to block the transmission of pain. So you may have guessed that for the general anesthetic, it sedates the entire body and you have loss of consciousness, while for the local anesthetic, it sedates a localized area and so you don't have a loss of consciousness. For the mechanism of action for the general anesthetic, generally, you have a synaptic block, while for the local anesthetic is usually a conduction block, right? So clearly it happened at the synaptic cleft there, synaptic region, and one occurs along the neuron, right? And so for the synaptic block, you have a decrease in the presynaptic calcium entry, and that therefore causes a decrease in the transmitter release. And there's also an increase in the postsynaptic hyperpolarization, and that's caused by an increase in the influx of chloride ions or the efflux of potassium ions. And for the local anesthetic, you have a decrease in axonal sodium ion entry, and therefore that causes a decrease in the action potential propagation. So for the route of administration, the general anesthetic includes both the inhaled and the intravenous drugs, right? And the local anesthetic includes the topical and the parenteral drugs. All right, so for the inhaled general anesthetics, well, it was back in 1846 where a Boston dentist by the name of William Morton, he demonstrated by using diethyl ether as a general anesthetic in a public demonstration. So as a result of that, the publication of the successful operation, it actually led to the use of general anesthetics by surgeons and ushered in the age of anesthesia. Can you imagine that? The first paper that described the use of the general anesthetic ended with the warning that its action is not yet thoroughly understood, and its use should be restricted to responsible persons. So, although it's been many years since that statement was written, the sentiment remains today. So, a lot of these anesthetics, we know what they do, but their action are not thoroughly understood. So, just to put the just in case you forgot the structure of diethyl ether, simple ether structure here. So for the mechanism of action of anesthetic drugs, and I kind of alluded to it earlier. So the pharmacological mechanism of action of the anesthetic drugs is not clear. The idea that we can understand the mechanism of action for a general anesthetic supposes that we understand what the term anesthesia means. And so a clinical definition of general anesthesia is a state where no movement occurs in response to what should be painful. Right? So your automatic reaction to pain is to move. And so the anesthesia is the definition, or the clinical definition is that of a general anesthesia is a state where there's no movement in response to what should be a painful situation. So although this gives us a working definition of the drug's action, it does not explain the physiology behind the action. Much research remains to be done on the physiological mechanism of action of these drugs. So what are the stages of anesthesia? Well, the first stage is analgesia. And that is analgesia without amnesia. The second stage is excitement, and that can be accompanied by nausea, vomiting, etc. Stage 3 is surgical anesthesia, so that is sleep, normal respiration, and blood pressure. And stage 4 is medullary depression, and that can lead to coma and death. So just to expound a little bit on these stages, well, the first stage, as we mentioned, the stage of analgesia lasts from onset of drowsiness to loss of eyelash reflex. So blinking when the eyelash is stroked. So that is how that stage is measured. And so that variable levels of anesthesia and analgesia are seen in this stage. The patient is considered unconscious at the end of stage 1. For the excitement stage 2, this is the stage where it's characterized by agitation and delirium. So during this stage, salivation may be copious, heart rate and respiration may be irregular. Induction agents are designed to move the patient through this undesirable stage quickly, right? And to stage 3, which is surgical anesthesia. And this stage is divided into 4 planes, and it is sufficient to understand that this stage of anesthesia is a target depth for the procedure, right? So that is where you really want to get to. During this stage, a painful stimuli will not elicit a somatic reflex or any autonomic response. And stage 4, which we mentioned, which is impending death, and I wonder why they call it a stage, but this stage lasts from onset of apnea to failure of circulation and respiration and ends in death, right? So anytime you go under any form of anesthetic drugs, it's serious business that we're talking about here. And we definitely want to get to stage 3, but not stage 4. So the ideal anesthetic combination will allow the patient to proceed quickly from stage 1 to 3 and avoid stage 4, right? And so the inhaled anesthetics are used in combination with other drugs to induce anesthesia. And so the drug combination used to achieve this are complex. So you might be wondering, what is the ideal inhaled anesthetic? Well, according to this source, and that is the text, the ideal inhaled anesthetic will be inexpensive, potent, pleasant to inhale, minimally soluble in blood and tissues, stable on the shelf and during administration, and lack undesirable side effects such as cardiotoxicity and other toxicities. And this part is interesting. The ideal inhaled anesthetic drug has not been developed yet. So who knows, you may be studying medicinal chemistry for a reason, so that you can be the first person to design and make this ideal inhaled anesthetic drug. So let's look at the structure activity relationships of the volatile general anesthetics. So as you know, if you look over here, you will see that there's no single pharmacophore for the inhaled anesthetics. And so the inhalation anesthetics in use today are nitrous oxide. So we see the structure here of nitrous oxide, halothane, which is here, isoflurane, which is here, desflurane, which is here, and sevoflurane, which is here. So the differences in structures here, so clearly there, well, these are ethers, right? So anywhere we see a C, carbon, oxygen, carbon, and derivatives of that, and then we have an alkyl halide here. So these are all derivatized ethers, and we have derivatized alkene here. We have a cyclopropane and nitrous acid. So these are, nitrous oxide. So these are all volatile general anesthetics. So let's look at, the studies that were done to relate structure to activity. So firstly, let's talk about alkenes slash cycloalkenes, right? So we know what our alkenes look like. We know that our cycloalkenes are rings. So as I mentioned earlier, this is an example of a cycloalkene, and this is an example of a derivatized alkene here. So the first SAR studies conducted independently by Mayer and Overton in the 1880s showed a distinct positive correlation between anesthetic potency and solubility in olive oil. So this was some early study here. So many series of compounds confirm this simple relationship, but exceptions to the model exist. And as with most things, there are exceptions. So the potency of alkanes, so these are the classes: alkanes, cycloalkenes, and aromatic hydrocarbons, right, increases in direct proportion to the number of carbon atoms in the structure up to a cutoff point. So what is this cutoff point? So within the N-alkane series, that's the straight chain alkanes, the cutoff number is 10. So the 10, which is N-decane, it shows minimal anesthetic potency. So in the case of the cycloalkane series, the cutoff number in most studies is 8. So the 8th one, which is cycloalkene, shows no anesthetic activity in the rat. And so the reduced activity of the compounds beyond their cutoff number could be as a result of problems getting to the site of action. And so you have reduced vapor pressure or high blood solubility, or inability to bind to the site of action and induce the conformational change required for anesthetic action. So here we're saying for alkanes, cycloalkanes, that there's a correlation between increasing the number of carbons with activity to a cutoff point. So we must remember our cutoff point of 10 for the N-alkane series, and a cutoff number of 8 for the cycloalkene series. So for the alkanol series, and that is basically alcohols, right? So the N-alkanol with a given number of carbons is actually more potent than the N-alkane with the same chain length, right? So that should be easily understood. The alcohol will be more potent than the alkane. So let's look at the effect of halogenation slash ether halogenation, right? So the first inhaled anesthetics used in the late 1800s, diethyl ether, as we mentioned before, and cyclopropane, it actually caused laryngospasms, which is sudden spasm of the vocal cords. So it did the job, but it had these side effects. So these compounds were also very explosive and flammable, requiring careful handling. And so the early studies found that halogenating the ethers decreased the flammability of the compounds and enhance their stability, as well as increase their potency. And that is why we see all of these halogens on or ether here, because they found that they were a better alternative. And also the higher atomic mass halogens increase potency compared to lower atomic mass halogens. So if we take a look over here and we compare isoflurane to desflurane, right? And the only point of difference is this carbon here and the chlorine versus the fluorine, and we're saying that the one with the higher mass, that is the chlorine, would be more potent than the one with the lower mass, right? And so, for example, replacing the fluorine with chlorine, as I said before, to form isoflurane increased the potency more than fourfold, right? So just changing an element from fluorine to chlorine, an element of higher mass, that increased the potency by 4. So that is significant. And going even further, replacing the chlor with bromine in the investigational drug, that increased the potency 3-fold further, right? And so that is some interesting research. In general, halogenated ether compounds also cause less laryngospasms than unhalogenated compounds. So that's an improvement, right? And so unfortunately, halogenation also increases the propensity of the drugs to cause cardiac arrhythmias and or convulsions. So that's not a good thing. So we get something good, but there's a drawback as well. So the halogenated methyl ethyl ethers were found to be more stable and potent than halogenated diethyl ethers, right? So we're looking at methyl ethyl ethers versus methyl ethyl ethers, which are these, in comparison to diethyl ethers, and I don't have any of those. So the halogenated, they're not here. That is the halogenated form of both. So the methyl ethyl ethers were found to be more stable and more potent, and I suppose that is why they're mostly represented here. The commonly used inhaled anesthetics are ethers or aliphatic hydrocarbons with 2 to 5 carbons. All right, so the effect of saturation. So molecular flexibility of the inhaled anesthetic is not required. In fact, you could add a double bond or a triple bond to these small anesthetic molecules having 6 carbons or less, and that increases potency. So addition of a double or a triple bond to small anesthetic molecules having 6 atoms or less increases potency. So it doesn't have to be a single bond, it can be a double or a triple bond. All right, so just to mention the injectable general anesthetic, so they're propofol, etomidate, and ketamine. We cannot necessarily make any structure activity relationships here, but just to mention that they are injectable general anesthetics. So that leads us to question 3, which is identify the more potent volatile general anesthetics of the pair. So based on the structure activity relationship that we just did, which one is more potent? So take a second and analyze them and answer the question. All right, so if this was your answer, then you are correct. So if we have the same amount of carbons and one has an alcohol and the other doesn't, the one with the alcohol is more potent. And we said increasing the carbon up to the cutoff point. So once we're below the cutoff point, if we increase the carbon, we increase the activity. So I suspect this would be more potent. And the same was true for the cycloalkanes. So the follow-up question 3 is categorize the following as injectable or volatile general anesthetics. So looking at the name, nitrous oxide, enfurane, propofol, ketamine, which ones are the injectable and which one are the volatile general anesthetics? All right, so that leads us now to our final section, which is the local anesthetics. So I have a diagram here of the proposed mechanism of action of the local anesthetic. So I'm going to walk you through, but just to read the caption here, which says A, and this is A, B, and C here. So A is the hydrophobic pathway into the nerve cell, so BAM, and B is the hydrophobic pathway to the binding site, so BAM, and this is the local anesthetic binding site, so BAM, and C, hydrophilic pathway from the inside of the nerve cell to the binding site, so BAM. Right? So what is the proposed mechanism is that these local anesthetics, they can be in the ionized form, the unionized versus the ionized form in vivo. However, in order to cross the membrane, it has to be in the unionized state, right? So it can actually go from the membrane to the binding site and cause blockage, or it can go straight through from the extracellular to the intracellular, and then once it's inside, it is protonated. So notice we have a tertiary amine here, and it is protonated, so this is clearly its ionized form, and then once it is protonated, it can therefore bind to the binding site and therefore block the sodium from entering the channel, right? So just to repeat, this is a proposed mechanism of action of the local anesthetics, and as we mentioned, there's the hydrophobic pathway that's this way, and B, another hydrophobic pathway, so it can come in and go here, as well as C, it can go BAM and then gets protonated and then bind to the inside of the nerve cell, and therefore creates this repulsive force and prevents the entry of sodium. All right, so this diagram is essentially has the same info, right? But because I, saw this picture, I thought it'd be nice to add this component to show that, the local anesthetics, the axon, that part of the membrane, and to also show that, you know, it's an intercepting, you know, the pain stimulus between the spinal cord and the pain stimulus. So it will act there, this portion of the nerve, right? And so you have the ionized form and the unionized form, and what we said is that it will basically be generally be protonated, but it be deprotonated, and it crosses the membrane in that form in which it is protonated to its active form, and therefore it binds to the binding site, which we're not seeing here, in the neuronal membrane, and causes blockage, preventing sodium from entering. All right, so for the structure activity relationship of these local anesthetics, well, the structure of most local anesthetic agents, they consist of three parts. So a lipophilic ring that may be substituted, so that is this ring here, and it could be, has, you know, one of the hydrogens could be substituted with something. It has a linker of various lengths that usually contains either an ester or an amide. So we must remember our functional groups here, and our ester or amide linker will be here. And then to top that off, we have an amine group that is usually a tertiary amine with a pKa between 7.5 and 9. So that is here. So clearly this nitrogen must be bonded to 3 carbons, which is why it will be a tertiary amine, right? So we have our lipophilic ring. We have our linker, which is usually contains an ester or amide, and then we have our tertiary amine. So for the aromatic ring, right? The aromatic ring, it adds lipophilicity to the anesthetic and helps the molecule penetrate through the biological membranes, as we saw when we looked at the mechanism of action, right? And so it is also thought to have direct contact with the local anesthetic binding sites on the sodium channel. Now, the exact amino acids involved in binding depend on the sodium channel being studied, as well as the state, whether it's open, closed, inactive, or closed active of the sodium channel, right? So this is the interaction that we're supposing would happen with the aromatic ring, right? So you have your van der Waals forces here for this section for the aromatic ring for the alkyl portions, right? And then you have the electrostatic attraction, for the charged areas. All right, so still on the aromatic ring, substituents on the aromatic ring may increase the lipophilic nature of the aromatic ring, right? And so a SAR study of para-substituted ester type local anesthetics showed that the lipophilic substituents and electron donated substituents in the para position increased anesthetic activity. And the lipophilic constituents are thought to both increase the ability of the molecule to penetrate the nerve membrane, as well as increase their affinity at the receptor site. So there's dual role there. So when the aromatic ring was substituted with the opposite electron withdrawing group, the electron crowd around the carbonyl oxygen decreased, and the anesthetic activity decreased as well. So important structure activity relationship seen here, where we need an electron releasing group, right? Electron donors increase polarization of the carbonyl group, while electron acceptors decrease polarization of the carbonyl group. So they'll pull electron to themselves. That's no good. We need an electron donating group, and I hope we remember our electron donating group in the para position that is ideal for increasing anesthetic activity. The nitrogen. So most local anesthetic, they contain a tertiary nitrogen with a pKa between 7.5 and 9.5, as we mentioned already. And so therefore at the physiological pH, which is about 7.4, both the cationic and the neutral form of the molecule exist. And obviously, as we mentioned, has to be tertiary. And at the physiological pH, both form. And remember, when we were looking at the mechanism of action, we saw both the cationic and the neutral form. For the linker, we said this already. The linker is usually an ester or an amide group along with a hydrophobic chain of various lengths. So in general, when the number of carbon atoms in the linker is increased, the lipid solubility, protein binding, and duration of action, and unfortunately toxicity also increases, right? So generally we have an ester or an amide along with a hydrophobic chain. And let's go back to here. So here we have an ester and a hydrophobic chain. That's what we're talking about here. So the number of carbons in this linker, so when it is increased, all of this good stuff happen, and unfortunately toxicity also goes up. So these are some examples of some local anesthetics, and it's really your job just to look at it and to identify, the structure activity relationship components, right? So we have our ring, we have our donating groups in the para position, we have our ester mainly here. Well, we have an amide here, and we have our hydrophobic chain, and we're seeing just CH2, 2 CH2s generally, and we have our tertiary amine here, right? So clearly our prototypical local anesthetic, and all of them seem to be related, are related in structure. All right, so our final question is, describe the proposed mechanism of action of a local anesthetic drug. So as we described earlier, so as we said also that at the physiological pH at about 7.4, we have both the ionized and the ionized version of these drugs. However, it is the unionized form which passes through the neuronal membrane, right? So that's one pathway. And then it is protonated within the neuron, and then it enters into the binding site here, and therefore it blocks the entry of sodium, and therefore carry out its activity to block pain. And as we said on the onset, it is a conduction block, right? And for the final question, it's saying design a local anesthetic drug. So having said all of that, are you able to propose a structure for a local anesthetic drug? So if you made it all the way to the end, thank you so much for watching, and see you next time.